He's the mission analyst currently for New Horizon. And in the past, Mark has worked on the Hubble Space Telescope, where he was instrumental in performing data processing and archiving, images for the Hubble.
Yep.
And
all the data.
In 2006, he was given the opportunity to hop aboard Messenger mission and payload and mission operations specialist with sequencing critical mission instrumentation and spacecraft commanding until the spacecraft's sudden demise in Mercury. And like I mentioned earlier, currently he is also working on New Horizons, and that mission is still going on, right?
Yep, and I'll be talking about that at 2.
He'll be talking about that at 2 o'clock. So make sure you come back for his 2 o'clock presentation. So I'm going to go ahead and turn it over to you, Mark.
All right then.
Let you start.
Well, welcome everybody. Did you get your lunch already? Nope. Did you want to get your lunch now? All right. This hour I'm here to talk to you about the Messenger mission. It's a mission that was sent to Mercury, and it was the second spacecraft to visit Mercury ever, and to this day remains the second spacecraft to have ever visited Mercury. So without further ado, why do we want to go to Mercury? Well, we wanted to go there because we want to test theories on the solar system. You know, the solar system scientists have all come up with various theories on things, but theories are great, but you need the applied data. So we wanted to get more data. Prior to 1970, we had only observations we could do from Earth. In the mid-70s, we had the Mariner mission go to Mercury, and we got some data. With Messenger, we got a ton more data. And we've learned that one of the great things about Mercury is it is the planet of extremes. Of all the bodies in the solar system, Mercury holds the gold medal for extreme action. Now, there have been a number of missions to most of the bodies in the solar system. Venus has had 43, Mars is 56. Asteroids, there's been 13 missions. There's been 12 missions sent to comets, which visited 15 of those comets, so several of the missions actually visited 2 different comets. Jupiter's had 9, Saturn's had 5, Uranus and Neptune have each had 1, and now the Pluto-Charon system has had 1. Mercury, at this point, has had 2 missions. So I mentioned that Mercury is the planet of extremes. It has the most eccentric orbit of all the classical planets, and we're going to go with the classical 8 and not worry about the Kuiper Belt for the purposes of this talk. It's the smallest planet. The orbital inclination is 7 degrees, which is more than any others. It has the highest temperature extremes of over 1,200 degrees from the coldest to the warmest points on the surface. And a short sidereal period, it's the only planet in the solar system that has a 3-2 spin resonance. So it rotates on its axis and revolves around the sun on a 3-2 resonance. It's one of the densest planets in the solar system. It has a dipole magnetic field. The only other rocky body in the solar system that we know of that has a dipole magnetic field is Earth. And it has the smallest axial tilt of any body in the solar system at 0.01 degrees, which is essentially perpendicular to its orbital plane. So Mariner 10, as I mentioned, was the first spacecraft to visit Mercury, and did this in 1974-75. It performed 3 flybys, and it got to image this much of the planet's surface. It did not see this, it didn't see a little bit there, because on each flyby, due to the orientation nature of the flyby and where we met the planet on these flybys as it was going around the sun, it always saw the same side of Mercury. It never got to see the back half of Mercury. And on each successive flyby, more and more instrumentation was failing on Mariner, so they didn't get to do all the wide field views of the planet's surface. Mariner was designed as a predecessor mission to a follow-up mission that was supposed to happen within 10 years. It didn't. It took over 30 years before we got Messenger going and launched. Yeah, I just covered all the slides on this point. So Mariner found a number of things that we were completely not expecting. From Earth, we're looking at a rocky ball that's orbiting the sun fairly close. and it doesn't exhibit any kind of atmosphere. We can't see anything of it. It must just be a dead world like the moon is just a dead, chunky world. What we found was a global magnetic field, which was completely not expected. To have a global magnetic field, you need to have a dynamo in the center of a liquid core, and it needs to be turning. But Mercury is rotating so slow as it's going around the sun, they still can't fathom how you can have a spinning dynamo there. It has the highest density of all the planets, as I mentioned earlier, and that was completely unexpected. It has a thin, rarefied atmosphere-exosphere. It's not thick enough really to be called an atmosphere, but there is a gaseous envelope that surrounds Mercury. And Mariner detected this. And Mariner was able to measure the temperature extremes on the surface from 840 degrees Fahrenheit on the surface in the early afternoon to minus 370 Fahrenheit in the pre-dawn hours, or pre-dawn days at this point. The Caloris Basin is one of the most famous basins, or most well-known basins in the solar system, and Mariner 10 found it, but only saw this much of it. The rest of it was in shadow every time Mariner 10 flew by. So from this, they had estimated the size of it. And this here is, this section here, you can see some of the details that Mariner 10 saw. You can see secondary impact craters that happened after the Caloris Basin formed. You can see these canyons here, these fossae. You can see these ridges. You can see pits all over the place. That alone is just a very interesting part of Mercury. But it's not the only story on Mercury. After Mariner 10 was done, there were people still interested in Mercury, so the only thing we had really available to actually study Mercury is the Arecibo telescope in Puerto Rico. And when they started doing radar studies of Mercury, they started getting bright points at the poles, these bright return things. They had no idea what this is. You've got this planet that's sitting next to the sun, and they said, the people who were studying this said, these reflect like it's water ice. But we're sitting at 0.3 AU from the sun. You can't have water ice that close to the sun and still be an ice. But this is what they saw. And this is all the data we had. So the Applied Physics Lab had proposed to build a spacecraft called MESSENGER. And MESSENGER is a convoluted acronym that stands for Mercury Surface Space Environment Geochemistry and Ranging. They chose MESSENGER because Mercury is the messenger of the gods. The proposal that was submitted to NASA was set up to answer these 6 questions. Why is Mercury so dense? What are the active volatiles on Mercury? What's the nature of the magnetic field? What's going on at the poles that Arecibo has these bright detections? What's the geologic history? And what's going on inside Mercury's core? To answer these questions, we had this set of objectives that we were to achieve. Image the entire surface in over 100,000 images, which we did in over 250,000. Do a complete survey of the magnetic field. Search for ice on the surface or evidence of species that could be from polar ice deposits. Map the surface distribution of the elements and minerals. Measure the topography, which we have a laser altimeter on board to do topography measurements, map the exosphere, and detect any irregularities in Mercury's rotation. So to build this spacecraft, we had to achieve some phenomenal technical accomplishments. One is building the sunshade right here. The sunshade is a ceramic Kevlar cloth. It's only a few millimeters thick that covers only this much of the spacecraft. The rest of this is open to space. The sunshade has to point to the sun the entire time, which dramatically limits how we can orientate the spacecraft. All the instrumentation is down here. The EPS, the GRNS, MLAs, that's the messenger laser altimeter, MAST, XRS, MDIS, all these instruments are down in this cone right here, and they point down this axis, perpendicular to this here. The two blue panels here are the solar panels that we have on board. Now, if we want to take and point these instruments at a feature or an area on Mercury, we have to be able to keep the sun in this zone. And we have 10 degrees that we can take and rotate the spacecraft like this to do that in, which is not a lot of room for us to wiggle around. Another challenge that we had was, as you notice, all the instruments are pointing in the same direction, but not all the instruments want to study the same thing. Some instruments actually want to point off the surface of the planet. They want to study the exosphere, which means we have to rotate the spacecraft to point off. If we do that, then none of the other instruments are studying the surface. So there's a conflict there because we have no pivots on any of these instruments to look in two different directions at the same time. But the science teams work and play well together, and we got all this worked out. The sunshade also, well, the front part of the sunshade was over 300 degrees Fahrenheit. The back part of the sunshade was basically room temperature, 70, 80 degrees the entire time, except at certain points in the orbit, which I'll mention a little bit later. The solar panels. These are the solar panels here, folded up against the spacecraft. These are the folks in the clean room getting ready to put it on a vibration test. The solar panels, as you notice, are actually 2/3 mirrors. And the solar panels are also fully articulable, so they can turn to be face on, or they can rotate 95 degrees off of the sun spacecraft axis. And while we were in orbit, we had them rotated like 70, 80 degrees off of the sun because it was so hot and we had so much energy, we didn't need to be full face on. When we launched and we were out at Earth's orbit, we needed to have the panels facing the sun the entire time to get the energy we needed. We communicated with the spacecraft using the Deep Space Network. There's 3 stations put around the globe for Deep Space Network. All spacecraft that are doing interplanetary work use these stations. There's one in Canberra, Australia. There's one in Madrid, Spain. There's one in Goldstone, California. They're approximately 120 degrees apart across the globe, which means we have a fairly comprehensive view of the solar system from any one station to talk to any spacecraft out there. And there's a fair few spacecraft out there. This is our instrument suite. Messenger was one of the first spacecraft to have this many instruments on it, just to study one planet. I'm not going to go through all the different instruments here, but this is the back end of the spacecraft. Most of the instruments are right here. The magnetometer points out here. Some I think it was 15 meters that came out. The solar panels are here. The fuel area is here. The main thrust drive is here, and then we have a bunch of other thrusters scattered around to rotate and work the spacecraft. The phased array antennae were there front and back so we could communicate with Earth depending on where Earth was relative to the spacecraft was relative to where it was in orbit around Mercury. There's a very, very complex geometry that we had to work with. Getting to Mercury, you would think wouldn't be that hard. I mean, it's right there. It's practically our neighbor. It's at closest approach, it's 0.7 astronomical units away from us. But it's also down deep inside the sun's gravity well. So if we were to send something straight to Mercury, we would pick up so much energy, we couldn't carry enough fuel to slow down to go into orbit. We'd just fly right past the thing. So doing a indirect orbital insertion wouldn't work either, because again, we'd be still picking up energy. So we had to do a convoluted orbit where we went around the sun like 17 times using deep space maneuvers, firing the main engine to change the trajectory and the speed of the spacecraft, do trajectory correction maneuvers, which are smaller, minor burns to do the same thing for a shorter period of time, and do flybys of Venus and Mercury to help slow the spacecraft down. Most of the time when you hear about flybys to planets, like the Pioneer and the Voyagers, when they flew past Jupiter and Saturn, they used it to speed up so they could get out to the outer planets faster, more quickly, and pick up speed. Here we want to use the flybys to actually slow down. So play a quick little movie. This will kind of give you an idea of how the orbits are going. Are you playing? So we launched from Earth here. Then we did a flyby of Earth. We used the Earth's gravity well to bend the trajectory a little bit tighter. DSM is a deep space maneuver. We had 5 deep space maneuvers where we fired the main engine. Venus 1 is the first Venus flyby. Venus 2 is the second Venus flyby. Mercury 1, Mercury 2, and Mercury 3 will be the 3 Mercury flybys that we did before we go into orbit. All of this took about 7 years. And there we are. Partway through that convoluted geometry dance with the planets, one of the spacecraft engineers came up with the idea of, say, we only have so much fuel on the spacecraft. We have the sun that we're getting closer to. We got these giant solar panels. Why don't we use the solar panels to work with the solar wind and try to use that instead of using the TCM thrusters and save some fuel over time? So they worked it out, and it turned out that if periodically we do like a TCM burn every 4, 6, 8 months, depending on where we were in the orbit. So if we started doing the solar sailing early, like 6 months out from when we would have had a TCM, the change in trajectory and course would be equivalent to that of the TCM, having that 5-minute or 10-minute burn. And it would save us that time, save us that fuel. All you got to do is make that little change early on and just keep making that change, and you keep that stronger impulse that you would get with the TCM. So the gentleman that came up with this, he also came up with how we were going to extend the life of the spacecraft, and he won the Robert A. Heinlein Award for his accomplishments with spacecraft and work.
How did that work, the solar panels? Did you use the energy from the panels or just the structure of the panels?
No, we used the panels, we could articulate them. So we used it to interact with the solar wind.
I see.
So March 18th, which is actually for East Coast time, was like 9:15 or 9:45, I can't remember now. On March 17th, we entered orbit around Mercury. And the orbit you see here was a highly elliptical orbit, extremely elliptical. It's perpendicular to the plane of Mercury, so it's tilted by about 82 degrees, so it's not completely perpendicular, but it's offset just a little bit. But at the closest point, we're around 200 to 500 kilometers above the surface of Mercury. At the furthest point in the orbit, we were about 15,000 kilometers away from the surface of Mercury. So up here, we got some great detailed images, except we were flying past super fast. So we didn't get as much as we wanted because if we took too long an exposure, things would blur out. Down here, we could take all the time we wanted because it took hours to get through this part, while it took 20 minutes to go through here. But you're 15,000 kilometers away, so the resolution is far lower than what we were up on top. But the idea of doing this orbit here was so we could study the North Pole, where we had all those radar returns from Arecibo. So I'm going to go through some of the mission highlights now. For the trivia bit, we've found a lot of dark reflectance material. This here is the equator for the magnetic field. This is the the rotation equator. This is where the magnetic field equator is. And you can see it's about 400 kilometers north of the rotation equator. And the science teams who are studying this suspect that sometime in the past, Mercury had gotten smacked really hard. They think it might have been a larger planet, and a lot of the outer parts of the planet were just blown off by whatever impact that it had suffered, leaving this denser inner part, and the core was shifted upwards 400 kilometers, which is unheard of. we have discovered over a dozen volcanic caldera on the surface, not active, but the evidence that they're there. As I mentioned, the offset magnetic dipole. We have the 4th and 7th largest impact basins in the solar system. We have this feature called hollows that we've seen nowhere else in the solar system, and I'll talk about those in a little bit. The 3 orbits, 2000th orbit was in May 2013. The 3000th orbit was in April 2014. The last orbit was, we did 4,104 full orbits of Mercury before we landed on the surface at a very high rate of speed. We took over 277,000 images of the planet's surface, and we determined that those bright points are water ice up at the poles, and I'll go through how the detector story of that came about. So this is the image compilation from Mariner 10. That's all Mariner 10 saw of Mercury. Our first flyby, we covered this much more of the surface. And the entire science team said, if anything happens to the spacecraft at this point, we've now paid for the mission. Because we've now discovered, we've doubled the information that we had on Mercury. But since nothing happened, happily, we got on the second flyby, we covered this much more of the surface. And on the third flyby, we got pretty much all the equatorial region. We just didn't have the pole regions fully covered yet. We would get that when we went into orbit. And this is what we have from orbit. North Pole view, South Pole view, you can still see there's some dark spots there where we don't have much information, and the whole equatorial section of the planet. Just a view of the planet. The North Pole's up here. This bright ray crater here. We had seen evidence from these rays that wrap around a third to halfway around the planet from this impact basin called Debussy. One of the things that we were doing when we were taking images of the surface, and why we have like 3/4 of 277,000 images, is we were looking at the surface in different phase angles of the sun. Like when you look at the moon through your telescopes, when it's in the early crescent phase, you can see all the shadows, you can see the mountains, you can see the craters really nicely. When you look at the full moon, all that stuff vanishes, but you see other features. So this crater is this crater right here under different phase angles. With the sun low in the sky, you can see all the craters that appear. You see all the shading and relief. With the sun high overhead, all those craters fairly disappear, but you see this dark material here. You see this bright material here. You see the rays, the ejector blanket from that impact basin, or impact crater. So we would take both of these two types of images to figure out how the surface of Mercury looks. These are looking towards the North Pole and the South Pole. The southern pole is heavily pockmarked with craters. The northern pole has much larger, smoother plains areas in them from huge lava flows like the mare on the moon. Because there's no appreciable atmosphere on Mercury, we don't have much erosion going on. So from the impacts of basins and craters, we have a lot of these secondary strings of craters from the debris that was knocked out. And it fell upon a number of grad students to figure out which of these impact secondary craterlets went to which major crater. I was not the grad student doing that. The center of the Calorus Basin, which we discovered with Messenger, was actually 10% larger than what they had estimated with the Mariner 10 data, has these radiating troughs or fossae coming out of it. This crater right here is called Apollodorus, and is actually a serendipitously superimposed crater right at the center, which is about right here of the Calorus Basin. It did not create these fossae, or these canyons. It just happened after the impact basin hit. Impact hit for Calorus Basin, filling it with lava. The lava cooled. As it cooled, it cracked and it formed ridges. These are basically the cracks from the cooling, and then this impact basin occurred. In other areas in the north, we have what we call ghost craters. This whole area is basically a big lava flow, and you see a fair number of small craters that are evident, but you can see hints of other craters buried under the lava flow here and here. And so they call these ghost craters. So the timeline goes back in the past. Mercury is heavily bombarded with a bunch of debris. And at some point, a lava flow had covered all that, and then subsequently new impacts occurred, but fewer of them, and smaller ones than the larger. This did not happen in the southern hemisphere. The southern hemisphere is just completely caked with impact basins. We also have a number of these ridges right here. This is called the Enterprise Rupees. It's about 3 kilometers tall, about 100 kilometers long. And they're scattered all over. 100 kilometers goes here and cuts down through here. This is the Carnegie Rupees here. It's about 5 kilometers tall and goes up through here. The color is basically a height relief. So the redder to white it is, the higher it is, the bluer to purple it is, the lower in altitude it is.
That's not the actual color.
Not the actual color, no, it's the false color. This is also a false color, but this is actually showing you the geological composition of this area. This is the crater Derain, and this dark area is what we call low reflectance material. And it's suspected that this is either impact melt, or this is material that was excavated from the impact and then just deposited itself in this area here. The bright light blue areas have other meanings, and then the red has different meanings depending on what you're trying to pull out. This is another, going back to the topographical coloration. The whiter, well, in this case kind of pinkish areas are the high areas. The dark purple here are the lowest points, and the range of relief from these two is about 10 kilometers. This is just looking at one of the dozens of volcanic caldera, just looking at the edge of the crater. You can see all these erosion features here where they've had avalanches. There's all avalanche here, and there's actually a little delta, if you will, of avalanche debris at the bottom. And this is the Caloris Basin. It's in false color, so it stands out much. It blazes compared to the surrounding terrain. And these orangish features right here are all volcanic caldera that we identified on the edges of the Caloris Basin. If you notice, the Apollodorus crater is right here. I can't remember what the name of this crater is, but it's a very, very dark crater. It's nearly black. And these three craters here are Munch, Sander, and Poe, which I will revisit in a short bit. Another thing we did was we wanted to look at the volatiles that are on Mercury and try to understand which ones are important and stuff. This is a potassium map, and this just shows where the greatest concentration of potassium is that we detected on Mercury. We also did studies for sodium and chlorine and other features, other elements such as magnesium and things. This was using the instrument that I mentioned. One of the instruments wants to look off the planet.
That's in the salt form, like potassium chloride or something. It's not pure. It's not elemental.
No, right. This is I mentioned earlier, one of the instruments wants to look off of the surface of the planet. It wants to study the exosphere. And this is scans from that instrument as it would wave cause the spacecraft to wave itself through space, scanning around and picking up these sulfur emissions. So the exosphere basically is right here. It's primarily a sulfur-sodium atmosphere, and then it would extend out 10 to 12 mercury radii pushed out from the sun, the solar wind of the sun. In addition to the sodium, we also had strong calcium, but the calcium only appeared, this is looking down on the North Pole, on the dawn side of Mercury. So it was like as Mercury rotated its back half into the sun would blaze off the calcium deposits, they would fall back and then fall back on the surface again as they cooled off. We also did studies with the magnesium that's in the exosphere, but I don't have a slide for that. This is just a chaotic looking view of the geographic composition of Mercury using one of the spectrometers on the spacecraft. It took very narrow slices of the surface of Mercury, just looking at very like 1-2 kilometer wide slices that were hundreds of kilometers long, and this is the map that they put together. They don't have this fully figured out yet, but you can see the Chloris Basin right here, and they can identify a lot of other things. Even after all these years, they'd have millions of spectra to go through. And a couple years ago, I got some time to try and help them, but they're so busy with other projects they weren't able to devote 100% time to trying to devolve all of this.
What graduate students?
I worked with one of the graduate students trying to help her out with this, and then she went off to, she had to go back to doing her other stuff. But yeah. The XRS, the X-ray spectrometer, was another instrument that we had on. And here we have the magnesium silicon and aluminum silicon readings from the instrument. This is the Chloris Basin right here. And you can see it's very depleted in aluminum silicon, but it's very high in magnesium silicate. We also determined from a gravity map that there's some very, very dense regions on Mercury in these areas. This is another false color map of Mercury. Like it pops out the Chloris Basin, and then you get some of these other impact craters with these large ejected blankets and rays in all directions. And this is a true color image of Mercury. It's mostly a brownish gray, but you can see some of the blues highlighted. They're there. They're faint, but there is blue on Mercury from these younger, fresher impact areas. How many of you guys are familiar with or watch The Big Bang Theory? A few of you? How closely did you observe this show in season 4? Let me recall for you, the apartment of Leonard and Sheldon, on their fridge had a Hubble photo of a galaxy. At some point in season 4, that photo disappeared, and that photo appeared. They contacted our mission operations manager, said, hey, tell us about your day in the life. What happens with the mission and everything? So he told us, and they said, oh, it sounds really cool. Can we have some of your images? And so apparently they put 3 images in the apartment. I have only found this one. It's on the refrigerator. A friend of mine said he found the other 2. He sent me a blurry close-up of the image. It's like, okay, I still can't tell where they are. But this is of the Beethoven Basin. And so and it's still there 6 seasons later. They haven't changed it out. I keep watching it. A period I turned on, it's like, yeah, they still have it there. They haven't put their New Horizons on yet. So, I mentioned the hollows. This is a new geographic feature that a geologic feature that we've never seen on any other body in the solar system. And these are it right here. This modeled terrain shows up as very, very bright areas on Mercury. And it kind of looks like it's just Swiss cheesed away down here. And there's been a number of papers that have been done on it, and I've been so busy with New Horizons that I haven't kept up the last few years, but I know I keep getting notices that another paper is being published about the hollows. But what they suspect is happening is there's a sublimation action going on, where the sun's energy is just sublimating this material away, and it just spreads out. And this is what it looks like false color. It is very, very different than the surrounding terrain.
We'll volunteer to go there and keep that.
I mentioned in the Chloris Basin the 3 craters, Munch, Sander, and Poe. This is the top of the Chloris Basin is very, very red. Here's Munch, here's Sander, here's Poe. You see Munch and Poe have very dark material around the rims. Sander has hollows that just absolutely litter the interior of it. It's just packed with these hollow formations. Moving on to other things, we have weird stuff that we've seen on Mercury. A couple of things I'll cover. This area, it's hard to see here. This particular area is basically just a jumble of irregular mountainous, hilly, hummocky terrain that we see nowhere else on Mercury.
What's sublimate?
Pardon?
What is sublimate?
Sublimate is
But what is doing it?
this the energy from the sun.
What element is coming out?
We don't know. Or I don't know. If they do know, I missed that paper. It turns out this was seen by the Mariner 10 folks, and they identified this as weird terrain. That was their technical name for it. Weird terrain. Nothing else on the surface of Mercury looks like it. It turns out this is on the exact opposite end, the antipode of the Caloris Basin. So something came in, smashed into Mercury, formed the Caloris Basin, the seismic energy went all the way around and met at this point, and just jumbled up the ground.
Time machine to capture that.
Yeah, it would be cool to have a time machine to capture that, yeah. Another weird thing we saw was this giant tooth that's sticking up. This is about 60 miles across, to give you an idea of scale.
No, it looks like the profile of a guy dead on Mercury.
But yeah, some people said, I don't see a tooth. I see Han Solo. So now we know where he's at.
Where's Java? He's probably in that crater.
Yeah. All right. I mentioned the ice on the North Pole. I want to give you the detective story of how we determined there's ice on the North Pole. Prior to Messenger, the only evidence we had of anything up here that was odd was the Arecibo radar returns. And this is the high-resolution radar returns. And you can see they look craterish in some places. Others, they just look weird, odd. And we had no images to superimpose on this to understand what it was until Messenger got there. And we superimposed the Messenger images over the Arecibo images, and every one of these yellow areas, which is the Arecibo bright return points, falls in a crater in basically what is a permanently shadowed area. The sun never shines in these areas. So that whole phrase where the sun don't shine exists here on Mercury. Remember, the actual tilt is 0.01 degrees. So you get permanently shadowed areas here. And recalling, Messenger's orbit took us 82.5 degrees tilted off of 90 so we could study the North Pole. So this is a view of this area here. Again, all the yellow is the ice, or the bright radar returns. And we weren't calling it ice at this point. Another instrument that played a role in this is a neutron spectrometer. If we were able to take a neutron spectrometer and just park it over the North Pole and focus here, we would suspect these areas would look like this. But because we're flying over the North Pole at a high rate of speed, this is basically what we got. But we determined from this that there's a fewer neutrons emanating from the surface of Mercury than there are out here. What would cause this? Water ice. If there's no ice, you would expect this kind of a flux, a kind of return across from the surface of the medium speed neutrons. If there's water ice, you would expect this kind of a fall off on the return. This is what we got. Follows it almost exactly. Very, very close. So another nail in the coffin of this is water ice, but we're not done yet. High-speed neutrons. Again, if there's no water ice, you'd expect this sort of return. If there's surface ice on the surface of Mercury, in craters, but on the surface, you'd expect this kind of a fall off. We saw this. splits the difference, which suggests there may be some surface ice, but there's also some subsurface ice on Mercury. That's just odd. So how does this work? We have cosmic rays that come in, penetrate the regolith of Mercury. Eventually they hit an atom. The atom, it releases a neutron. These neutrons then scatter all over the place. Some are reabsorbed, some go off into space, and we can detect them. That's what the neutron spectrometer is for, detecting these things. If you have a blanket of water ice, that will absorb a significant number of those neutrons and block them from coming back out. So that's where you would see the low-speed coverage. To have it subsurface, they've figured out there's probably 10, 20 centimeter thick layer of material over the water ice that's there. And another movie to show you. I'll play this again, but if you watch this crater here, this area right here never sees the light of day. Come on, where are you at? So watch that crater right here again, or any other ones you want, but that's one Mercury day. And this is that crater again. This is the area where we have the bright radar returns. This is closer to the actual pole itself. But all these spots here are permanently shadowed areas at the pole. Now we do a topography measurement. Again, the warmer the color, the higher the altitude. The colder the color, the lower the altitude. And you see Prokofiev crater, which is that one I kept pointing out, it's several kilometers deep, and the high points are really up in here. But that's not the end of the story. We have a laser altimeter that we were using to do the topography measurements, but we can also measure the intensity of the beam that came back to the detector from the laser. And we understand what the surface of Mercury is basically composed of. We understand the reflectance of it, so we understand how much of a return we should get from the laser. These red areas actually set upwards of 50% more return than we would expect. The much more highly reflective areas on Mercury, and they superimpose on all those bright areas, which is surface visible ice. We also did temperature measurements. All these blue areas are super cold. They're in the 100 to 100 degrees Kelvin, which is pretty chilly. You want a sweater or two. And again, and the warmer areas are all exposed to the sun at one point or another and are much, much warmer. So how does all this come about? Well, you have a crater here, and you have these permanently shadowed areas. 80 Kelvin here, 350 Kelvin over here. You have a comet come in, bumps into Mercury, leaves behind, the comet's basically a dirty ice ball, a snowball. For intents and purposes, these black spots here are the impurities in the comet. The white is the water ice. You see the angle of the sun here cuts across that field and starts sublimating away the ice. As it sublimates away the ice, the impurities start to condense and congeal, forming a blanket which covers some of the ice, but the ice over here, which never sees the sun, stays exposed to space. And at these temperatures, water ice is stable for hundreds of millions of years. It will never disappear. Towards the end of the mission, we started doing more radical things with the spacecraft because we knew we were going to lose it eventually. We might as well just go for broke and do what we can. So we started doing longer exposures of the craters, and we couldn't do too long exposures because again we're flying past this at quite high speeds. But we could take and stretch the images. So this area here is just completely blown out, but this is this permanently shadowed area here. We can see it from the reflected light off of the crater rim from the other side of the crater. The South Pole also has permanently cratered areas, but again, if you remember the eccentric orbit that we have, we're 15,000 kilometers away. You have to be 1,000 kilometers or less for the laser altimeter to even begin to get radar returns. This is the best we could do. But there's permanently shadowed areas down there, so we suspect there's a like amount of water ice down there. The last I talked to someone about the water ice, it's been a few years, they had estimated that you could do a column 2 miles tall, the diameter of Washington, D.C., and that would be how much ice is up there on Mercury. So we can bury Washington if we want. All right, Messenger. Messenger was determined, it was preordained it was going to land at like 3.7 kilometers a second onto Mercury's surface. So we would be doing something we call litho braking. Litho being the surface of the body, and braking meaning we're either stopping or braking and that we're busting up the spacecraft. While we were going around orbit of Mercury, we would periodically do what we call OCMs, orbital correction maneuvers. Didn't do them too often, but they were built into the orbital plan. Because the orbit of Mercury, orbit of Messenger, if this is Mercury, the orbit would shift slowly and start to come down. So we'd have to have an orbital correction maneuver to boost it back up. So we could keep this elliptical orbit. And over time it would drift down and we'd have to boost it back up again. So we had these OCMs planned. But we only had so much fuel. Eventually we were going to land on Mercury's surface at the end of March. So each OCM here is when we would boost the altitude of the periaps, the closest point of Messenger's orbit to Mercury. And we would run out of fuel around OCM 12. And that would be that. However, the gentleman I mentioned earlier who came up with this idea of solar sailing and actually applying it to the spacecraft also came up with the idea and said, hey, you know, we use hydrazine as our main propellant. We do not like to use hydrazine because it is extremely volatile. Who saw The Martian? A few of you guys saw The Martian. Do you remember when he was trying to extract water out of the hydrazine from the rocket fuel and it suddenly blew up on him? Highly volatile. You look at it cross-eyed, it blows up. So anytime any space mission, and that went from Messenger, that goes from New Horizons, any space mission out there, they have to fire their engines, they're nervous as hell because it could blow the spacecraft up. So far, that's happened only a couple times ever. And not on anyone I worked on. So we were going to run out of hydrazine sooner or later. We used gaseous helium as a pressurant to push the hydrazine into the nozzles to have a fire. Well, once we're out of hydrazine, what do we have left? We have this gas, this helium gas. Helium gas really doesn't burn real well. We don't have the mechanism to use it as a fuel. But he did a calculation and said, we can still use the gas to push the spacecraft up some. Just pressure. Opposite forces in different directions. So we could move the end date of Messenger from end of March to a month later, at end of April, but that's a month more time we would get out of it. So we had OCMs 10, 11, we run out of hydrazine here, we push it back up, we start dropping down, and we would impact down here, but with the using the cold helium gas, we were able to bump it up a number more times before we just couldn't do any more to it. And it worked. March 28th, this is where Mercury and Earth would be relative to each other. This line is the orbit line of Messenger, and Messenger would have hit the backside of Mercury relative to Earth at that time. With using the gas, we were able to extend it to its here, but it wasn't quite enough where we could actually witness the impact. It would still go on the dark side of Mercury relative to where we could see it from Earth. And what we had to do was monitor a signal that was coming from the spacecraft, and then we see it go behind the Mercury, and if we didn't see it come back out again, we knew we did it. And if we saw it come back out again, we knew we missed. We did not miss. Impact is right here. It was at 1925 UTC, Universal Time, so subtract 5 hours for East Coast time, on April 30th, and we hit this spot here. So there's a new crater right about here. They estimate it's about a 15-meter large crater. We haven't been able to see it because we have nothing there to view it with. However, the European Space Agency is working on a mission called Bepi Colombo, and any year now they will launch. They've had a lot of problems getting some of the instruments get their stuff in on time, and they should have launched already, but they haven't yet. But Bepi Colombo is going to, it's a combined mission with JAXA, the Japanese Space Agency, and they're doing a 2 spacecraft thing to Mercury. And one of the things they're going to look for is a new spot right here, new crater. And why? Is because this is going to be the freshest, newest impact crater we know of on Mercury, and we can get some new data on the subsurface elements and information at this point. This is the first image that Messenger took of Mercury during the first flyby. This is the last image we got from the spacecraft before it disappeared. And that was our last team photo. I'm hiding in the back. So any questions?
Where is that?
This is in the Mission Operations Room.
Where?
Oh, at Johns Hopkins University Applied Physics Lab.